Okay, so good afternoon. We start today's session on time. So you remember in session one, we have studied some basic knowledge about robotics, all right? And if you think about the application with the use of a robot, the first scenario should be industry automation, right? Because you could find many robots in production line, right? So therefore, it is always good for you to know what is a production line, what is industry automation, right? So in today's study, you will know, right? Manufacturing industry, inside there we have automation system. Then inside automation system, we may have robot system or other automated equipment. Then inside all the automated equipment, you will see control system, right? So it means behind automation at the basic level, you must think in terms of control system, right? So today's study is extremely important, extremely useful, right? So the knowledge about the control will not only apply to robot, will also apply to other type of automated equipment, right? So this knowledge is extremely important. And normally for our students, they will at least spend 1 or 2 semesters to study today's concept, right? Because we will go through manufacturing process. Even for manufacturing process, our student will spend 1 semester to study all these process, all right? Then for control theory, our student will also spend another semester to study control theory. Then for you, you just spend 3 hours, you will gain the exposure to these 2 important domain of knowledge, right? Okay, so for today's session, we will have 3 parts, right? First part is for you to know what do we mean by industrial automation. Because when you talk about the automation, people may talk about the office automation, right? So when you use a software like a PPT, Word, that should be the tool for you to achieve office automation, right? But here, by default, we talk about the industrial automation, right? And when you think about the automation, then you may want to know what to automate. Automate means what? To automatically control certain parameter or certain variable, right? So automation is closely linked to control. So therefore, you need to identify inside the industrial process what could be put under the control of a control system, right? Then once you have a control system, then you will want to know how to design the control system. Okay, just now one of you asked this question. Okay, what do we mean by 4? Okay, yesterday remember I asked you to pay attention to this 1, 2, 3, 4. 1 means 1 system, 2 means 2 output. Okay, steady state response, transient response. 3 means 3 KPI, right? So you have stability, response time, response accuracy. 4 means what? 4 design methods for you to achieve the best control outcome, right? Okay, so this will be the 3 parts for you to study in today's session. Okay, so let's start with the part 1 for section 2. All right, what is industrial automation? Okay, and in order to know industrial automation, or in order to know automate the equipment, you need to have a top-down view, right? So at the highest level in industry, we have a manufacturing system. Inside the manufacturing system, then we have a production system. So you see the two keywords, manufacturing, production. Then it is inside the production system, we can talk about the automated equipment. The inside automated equipment, then there is a control system. Then you see the roof, okay, sensor, control, actuation. Actually, this is a feedback control roof. And at the bottom, you see these two keywords, automation, control, etc. Right? So normally our students will spend one semester to study all the concepts which are related to manufacturing, and then another semester, okay, for the study of control theory, right? But for you, we only have 3 hours to go through all these major concepts, okay? So I quickly help you to understand what we mean by manufacturing system, what do we mean by production system, and then look at the input to production system and the inner process inside the production system, right? Subsequently, then we try to identify the key parameter or key variable which could be put into control, right? Okay. So now we try to give a top-down view, right? And here, if you want to translate manufacturing into Chinese, and I guess all of you know, okay, this means 制造, right? But if I ask you to translate production into Chinese, normally this should be 加工, right? But then you look at in the media, all the newspaper always say that China is a big country for manufacturing. But actually, this is the wrong statement. Okay, we don't even know why. Okay, manufacturing include design, production, and the marketing and the sale. And then you understand a lot of products produced in China are not in design in China, right? So strictly speaking, China is a big country of production, right? Clear? So try not to confuse. I hope after today's study, you will not mix up the meaning of these two keywords, right? Okay. Then what is manufacturing? Then this here we will give you an overview.
On a piece of paper, delicate lines, smooth shapes, the perfect marriage of great design and classic engineering.
The days are over that design can just do a design and engineers figure it out. We now produce and develop cars, in 3 years' time. That's very fast. And when we do that, when we as designers communicate with the engineers.
Bring a car to Lowe's, like the baby in the world. Man can do it wrong, but can't do it wrong. And then do it wrong, go forward.
It's taking years, but designers and engineers at BMW are close to turning that dream into reality. They invented prototypes of the car. Now mass production is about to begin, what BMW has been calling the E63. The rest of the world will soon know as the 645 CI. The BMW headquarters are in Munich. The new sports car will
Okay, I don't know why. Okay, so this video actually give you a quick overview about the nature of manufacturing. So in the video, you see the design phase. There's an engineer who sketched a new car, right? And also you see the mock-up of the prototype, right? Build up the prototype. That means the first model of design the car. Then subsequently in the video you talk about the mass production, right? So after that, marketing and sales, etc. So you see, manufacturing include design, production, logistics means sales. You may have an inbound logistics to mass produce a car. You need to buy a lot of components, material, etc. Right? Outbound logistics means what? Once your car has been produced, you must sell your car, right? So you have a marketing and sales, etc. Okay. So this is the meaning of manufacturing. Production is just part of manufacturing. Understand? Okay. So manufacturing actually is a system. Inside you have a lot of subsystems. So you see relationship between manufacturing system and the production system, right? So manufacturing and the production are not the same thing, right? Okay. So when we talk about the manufacturing, when we talk about production, we must be careful, right? Okay. Then this slide gives you overview about the different system inside manufacturing system. So on top, okay, you have a manufacturing system. Then this slide include design system, production system, business system, right? And the inside production system, then you will see a lot of process and also quality control system, manufacturing support system, right? But in particular, you will see automation system and control system, right? So this slide helps you to understand the relationship among the manufacturing, production, automation, and control, right? And you will see inside the product manufacturing process, we may be able to deploy robot or automated equipment. Okay, so this helps you to understand, okay, relationship between robot and automation and the control as well, right? Okay. Then for the design, this is an illustration. For example, you have an idea about the new type of humanoid robot, assume in your brand, you suddenly come out with this idea. Then you need to translate your idea into the detailed drawing, right? So pay attention to the upstream of this diagram. This we call upstream, this is the downstream. Inside the upstream, so basically you have an idea about the new product, and this new product consists of a key system, Each key system may have a lot of key components. Then you come out with a detailed design of all these key components. Once you have a design drawing, the downstream means what is production already. Okay, either you purchase a key component from the supplier or you in-house build all these key component, right? And pay attention to the last phase in production. The last phase is always assembly. So assembly is always the last phase, right? Inside the production line. So through assembly, then we will produce a ready product. So after that, we trigger the marketing and sales. Okay, so this entire pipeline basically help you to understand the nature of the manufacturing, right? And here is one more example. Now you see this is the diagram from Boeing, right? So this is the manufacturing, okay? From the concept about the new airplane, then you translate this guy into the drawing. Look at the upstream in this pipeline. All these are the part drawing, right? Then downstream should be the manufacture of the production of individual key component and assembly of all these key components into key system until you obtain the final product, etc. Right? So that helps you to understand the nature of manufacturing. Then what is the nature of product design? And here I just showing you one example. If let's say you want to produce a smart robot as a product, maybe you have an idea about a new robot like this. Okay, this robot can move has a mobile base, has an arm, right? And also has a gripper, and also has an eye, camera, etc. Right? So then you need to list down the functionality which could be performed by the robot. You see all the yellow yellow box basically indicate the functionality of this robot. Okay, then you see all the line drawing, but pay attention. Now we have signal flow, energy flow, material flow, etc. Right? So based on all this functionality, for example, mobility, manipulation, grasping, perception, etc., communication, then you may have a possible solution. They say for wheel mobility, what kinds of wheel, how many wheel are you going to equip this robot? Okay, what should be the layout of all these wheels, etc. Then you come out with this table. This we call it as a morphologic chart, right? Then this table will give you all kinds of combination, even for the arm, how many limbs, right? For the hand, how many fingers, and the appearance, how will this robot looks like, etc. Right? So you have a lot of options for each functionality. Then among all these options of each functionality, then you have a lot of different versions of a combination. Here I just use 3 examples. Combination A, B, C. Then you need to define criteria to do the evaluation, right? Let's say mobility, stability, cost of production, and appearance, whether it looks good or not, how easy it is to do assembly, to do maintenance, whatever, right? So you do the score, then you find the one which if you use a higher score, then this combination should be the solution chosen by you to come out with the design of this product. Then you just implement this combination B, right? Then you will have a 3D view of your product, then the part drawing of your product. Then for each part, then you will decide whether you are going to produce the part in-house or purchase the part from the supplier, right? Okay, for those of you who are doing the study in mechanical engineering school, you will know all this detail, right? Okay, but in case if you are not in a school which will teach you how to design machine or product, I guess if you can understand all these slides should be good enough. These are the basic guidelines you will go through in order to come out the best solution for the design of any machine, right? This is the procedure for you to follow for the design of any machine in the world, right? Okay, and then you may want to know what should be the input to manufacturing system, right? Just now you see, okay, you have all the part drawing. So part drawing should be one type of input, but this input should not be good enough. You still need to spend energy. You must also know a certain knowledge about the process which you are going to operate in order to produce all the design the work piece. Work piece basically is the part drawing, right? All the design the part inside of the product, right? And the sum of the design of the part could be purchased from the market. Then we call them as a component device. It means you can purchase from the supplier, etc. So you see the input to the manufacturing system include many things. Then output from manufacturing system, it depends the type of manufacturing company. Some company may just produce a component device as a product, and this component device will be used by another manufacturing company. Okay, so normally all the company will form a supply chain, right? So just now you see this logistic terminology. So basically means we have a supply chain. Usually you have a big supply chain, right? Company A supply product to company B, B supply product to company C, C supply product to company E, etc. So you have a big supply chain, right? Okay, so this gives you idea. It's only one company at the end of the supply chain that will produce the final product to the consumer market, right? Okay, it's just for you to know. Then they want to know, okay, how to transform input into the output in manufacturing system, right? So that means the manufacturing system has an input, manufacturing system has an output. How going to transform the input into the output? Answer is we need to operate the processor, okay, inside the manufacturing system, right? Then here you see this three appear here, right? So we want to operate each process as stable as possible, as accurate as possible, as fast as possible. Even three already there. Okay, that means for the inner process which transform input to the output, again we have a three KPI: stability, accuracy, response time. Right here. Okay, but for the detail of the process, we will study in detail in the subsequent slide. Okay, so it's not worry. Okay. So once we know, okay, manufacturing system include design system, production system, marketing and sales, right? And the design system is also quite complicated, right? Then for the production system, we have a lot of inner process, etc., right? Some of the input to production system may come from the supplier, etc., right? Then what should be the blueprint of any company in the whole world? I do not know how many of you have seen this one and how many companies know this slide. This is the blueprint of any company. So you remember yesterday when we talk about the robot, when we talk about the design of the robot, you see this blueprint of any robot genre. I'm showing you. Okay, you remember you have a task, you have a motion planning, kinematic dynamics control, body, etc. That is the blueprint for a robot. Then what is the blueprint for any manufacturing company? Answer is this one. Okay, now you see logistics, we have an inbound logistics, we have an outbound logistics. Then logistics actually form the key component inside the supply chain. Just now I use this big supply chain, right? If the final product is very complicated, like an airplane, like a car, etc. So for the supply chain of aircraft, normally you will see this is a very, very big, very long supply chain, right? Okay, so then you see inside any company, the core component should be for production line. But inside the production line, we have a lot of process, right? Then among the process, you need to transfer the output from one process to become input to another process. Now you see transportation. This is the inner transportation among the old process. Okay, so in order to operate this, on top you see we have a process control, equipment control, material flow control, right? Then you see all this equipment interface, right? Then you see all this equipment, right? And some of them could be robot, material handling equipment. It could be a robot. So inside here, you can identify the opportunity for you to deploy a robot to serve as an equipment, right? So we lump all this together. You see this big box there, and this is a very big name, important name in industry, MES, right? We call it as a manufacturing execution system. But actually, this could be the easiest way for you to understand MES is just to consider it as an operating system of a factory. You know, inside the computer, we have operating system, yes or no? Every computer, even inside your handphone, you have operating system, OS, yes or no? So MES is what? Just OS or factory or somebody, but they use this MES, and some of you get lost. Right? Well, what is MES? Actually, it's the operating system of a factory, somebody. Okay, and then okay, the important thing is we see your computer, even your handphone, you can play games. Game means what? It's simulation, right? Another terminology, simulation. Your computer, you can play game, yes or no? Game means what? Simulation, right? But of course, in the factory, you cannot play game, otherwise, your factory will lose some. If you do not produce product, how can you survive with your company? How can you hire so many workers, right? So inside here, you cannot see you play the game, but from a technical point of view, they are the same thing, right? So you need to have a simulation software to look at how your product looks like in the virtual space, how is the process looks like, how is your operating system looks like, right? And then eventually, how is your supply chain looks like, and then eventually, how is your entire factory looks like, okay? You see the big level here, we call virtual manufacturing, or you use another term, digital twin of your factory, yes or no? I guess some of you heard of a digital twin, right? Okay, so it's the same inside your handphone, you can play the game, inside your computer, you can play the game. But inside the MEMS, you can also have a simulated version of your factory. Okay, so this looks like very much like a brand. You can say this is the brand of factory, right? So computer is a brand. You can put a computer on top of a robot, right? Or inside the car, essentially. Here. So this slide is actually important for you to understand the blueprint of any company, right? Okay. But for us, we need to zoom into some specific module. Otherwise, you will spend one semester to study all the detail. Okay. But here we just pay attention to the factory operation and the input to the factory, because input to the factory comes from the output of a design, and also need a bit supply chain, you need to buy the component material, right? Then output from the factory operation is go to the marketing and the sales department. You must sell your product to the market, etc. Right? Just pay attention to these three modules, because the rest remaining are just supporting system. Okay, so if I zoom into the more detail, then immediately you know, okay, this is the production system. Input to the production system, assume that we are going to produce all the key components in-house, right? So then you have a product drawing. Product drawing means part drawing, all the part drawing, right? Then we have a material, right? So then you see production system just transform input material according to the requirement from the drawing all the way for finished product. Finished product may not be the product for consumer market, right? It could be the component device for other companies, right? So always think in terms of a supply chain, right? Okay, and then inside you will see opportunity for you to do automation control, right? Okay, so then what is the product design? Product design means the drawing of the product design. Then this is the output from the design. So you should not think that we only have one drawing for one product. Actually, it's wrong. Okay, so normally you have many key components, many key components. All right, and the design drawing will also tell you relationship among the key components. How are you going to put all the key components together to form a key module, key system, and final product, etc. Right? Yeah. So once you have input to the production system, first thing to do is to do the product making planning, right? You need to know where to buy the key component, indicated by the designer. Okay, designer say, okay, this key component just buy from supplier, no need to in-house make, right? Then you need to schedule a plan how to do the purchase. And some of the key components are produced in-house. Then you must plan how to produce all these parts. Then you see you have a yearly quantity, monthly quantity, weekly quantity, daily quantity, right? Because all these information are needed by the marketing and sales department. They don't really see the mathematics, right? Okay, because when you produce a part or produce the product, you want the product to be purchased by the buyer. If your product has no buyer, then why are you going to run a company? Understand? Okay, whatever you are going to produce must be purchased by someone, right? Okay, then what should be the material input to your production system? Okay, this slide summarizes the popular engineering material used in mechanical manufacturing industry, right? So you have metal, I guess all of you know, ceramics, polymer is also a popular one. And composite, today we have a lot of composite material, okay? But to understand material, I guess you need to spend one semester, at least one semester to study all these things, okay? But you know the name is good enough, right? So once you have the input, how to transform the input into the output in production system? Answer is what? We use inner processing. And in manufacturing, now you see we have a big family of a process to use, okay? And we cannot go through all of them. I just pick up a few popular ones, okay? Solidification is very popular, deformation is very popular, material removal is very popular, right? Welding is very popular, and then assembly, okay, here is very popular. Okay, these are the major process for you to know, okay? Then once you plan the product making process, then you will also need to know for each product, okay, because product making planning is to know on daily basis how many parts to produce, right? Then for each part, you need to decide how many process to use, okay? This is in general, one product may involve in maximum 4 process, right? So you have a basic process, secondary process, property enhancing process, finishing process. In maximum 4, but some of them may be 1 or 2, okay? So it's up to you. So then in this case, what should be the basic process? You have all these options to choose. Secondary process, from this table, you can choose one of them. Property enhancing process, choose one of these 2. Then finishing operation, okay, you choose one from this column, right? Okay, so once you know on daily basis how many parts to produce, for each part, how many process will be involved, right? Then you need to come out with this schedule of work schedule for each part, right? So you see, this is to manufacture a valve, 1,000 watt, right? Then you look at the machine involved in making this part. You see, you have a machine number 325. 325 we use 2 times. Machine 114, machine 240. This guy we use 2 times. Look at the name of the process. Slowly we will go through, showing the video of drilling, milling, and this is also turning. You see, turning process. Phase. This is also turning process. Okay, these are the material removal process. Then you will use this time, this machine. Duration, you see, setup time, cycle time, setup time, cycle time, etc. Right? But this is just for you to know. Okay, to produce each part, you must come out of all the detail, right? So which machine to use, how long you can use to set up, 1 hour to set up. But machine itself only operate on each part 8 minutes, not very far. You see, you spend more time to do the set up than doing the actual machining, right? We just help you to know, okay? And this video help you to understand, right?
Soon about to be assembly line. One shop. Roman DG is manufacturing everything from industrial printers to milling machines to vinyl cutters, using a single worker to assemble a product with thousands of parts from start to finish. Each one-person work stalls, however, a lot of digital power. A range of high-tech gadgets from 3D graphic monitors to digital screwdrivers help workers make every one of the company's 50 products.
約2日間にわたって見立てに必要な基本的なスキルを身につけている人を専用に設けられたブレーキによって行います。研修後は比較的短時間で組み立てすることができる小型のプリンターや小アセンブリ、つまりユニットの組み立てから始めてもらいます。組み立てするにあたって、ネジリーブルの小マシンに関しては、部品とフラッグから取り出します。で、取り出すと、このフラッグが、ドライバーで実動するように、
The computer keeps track of every step, ensuring correct components are used and the correct number of turns are applied to the screw. Workers' speed and efficiency are monitored, and bonuses are awarded based on productivity.
そのパソコンで記録された合計の適用の時に、早い時間作業というところは、どういった工夫がされているのか、関係性があるのかというところを、現場を管理しているスタッフの中心になって、その膨大なデータログを使って、しっかり分析して、分析した結果を教育であったり、実体パソコンの画面でこの使える採用しているコンテンツの方に落とし込んで、全員の底上げをして、バランスを抑制したりという活動を
While cell manufacturing, as it's called, isn't new, Roland DG says the use of digital gadgets speeds up production time, lowers defects, and helps to keep workers motivated in a market crowded with competitors. At the end of the day, the computer displays the time it took to complete the job, and it even gives workers a pat on the back,
お疲れ様でした。
which means you must be tired, and we thank you.
Okay, this should be good enough. So from the previous slide, you know, okay, input to production system includes the part joining plus engineering material, right? And then inside the part joining, you know the relationship among all the parts. The relationship among all the parts basically tell you how to do the assembly, right? So either you can purchase all the key components or in-house produce all these key components, right? Once all these key components are ready, then the previous video showing you the last activity in the production line is to do assembly, right? So you can hire a single person to do the assembly, okay? And or you use a robot, you can start singular, okay? We deploy a humanoid robot to replace the girl, okay, inside the video, okay? You see all the girls are doing assembly tasks, okay? So this helps you to understand that the assembly should be the last activity inside the production system. Right here, okay. Then you can keep this question in mind about how to produce a key component. Later on, we will see all these typical manufacturing process which allow you to produce all these key components. These key components are needed for you to do final assembly, right? So now we look at some basic knowledge about the production system itself. We start to go into the production system, right? And based on the knowledge in the previous slide, I hope you know roughly what is manufacturing, right? And the inside manufacturing system, you have a production system. Then this slide or this video will give you a very quick overview about the entire factory in the automobile industry. Okay, this may be good enough for you to have a rough idea about the production line in which you will see the assembly activity occurs, right? We can also use production line to operate a lot of process, right? Then this slide basically summarizes production line inside automotive industry, right? So you can identify, you see the body shop, and okay, and material transport system, etc. Right? Engine, transmission, etc. Okay, so this just give you the idea about the complexity inside automobile industry, etc. Right? Okay, so then you may want to know what is the typical layout of a production line. Okay, so you may have this linear arrangement of automated station. You see, AUT means automated station, or you may have this kind of layout. You see, you have a multi-loop genre, and if you pay attention to the flow of material. For this one, you can only flow in one direction. You cannot come back, right? So because it continuously flow from left to the right. But for this one, you have more flexibility, John. This material flow here, then eventually can come back, right? Once you reach here, you can always come back, right? So this is more flexible, but this is more complicated, right? So it's just for you to know. If you want to have a more flexibility, then you have this matrix layout, right? That gives you more flexibility for material to flow in different directions, right? So one material can repeatedly come back again with the same automation station, right? If you pay attention to the research in manufacturing, I guess this may be the future scenario, right? Because in the old days, it is very expensive, and you need to have an AI for the brand of a factory. You need to have a high level intelligence to do the planning of a material flow inside among all the automation station. Okay, just help you to understand. And this will help you to understand in the case if the product is very bulky, very, very big. So instead of moving the material, moving the key component, in this scenario, you see, automated equipment is always fixed. It's only the work piece move along among the automated station. But for this one, you see this product is huge, right? If you move this huge product everywhere, you will waste a lot of energy, right? Another way is to move your automated station, right? You see, your product is fixed, but your process is moving. Okay, based on the need, you move in, you move out, move in, move out, right? Something like that. Okay, it just help you to know. And then this is a typical scenario. Okay, this is also a production line. We transform the rock into the final product, which is a powder or cement, right? So you see the range of transformation of material. But it's going to help you to understand mechanical manufacturing basically to transform input material into the specific geometry and the output, okay? So input is a solid in the form of a rigid body, the rod is a solid in the form of rigid body, and the output is also a solid, but in the form of what? Powder, right? Powder is a solid material, right? Okay, so this can help you to understand that conceptually it's very simple. Your material, the input has a geometry, and the output has another geometry, right? That's it, okay? Change the geometry of the material, that's it, okay? So then, based on the previous slide, then you can define what is a production system. So a production system maybe consists of a series of automated equipment, automated station for the purpose of transforming the geometry of the material at the input into the desired geometry at the output. That's it, right? Okay, so this is a production line. Okay, and since we need to transform the geometry of material, the input into the desired geometry at the output, then we can achieve this objective either by employing human worker or employing machine. But workstation in general, maybe a person operating inside here, or a robot inside, or automate the machine. From here, immediately you understand, okay, the need for automation, the need for deployment of a robot, right? So you see, today's study is also related to section one. Section one talk about the robot, right? Then you can find the opportunity for you to deploy robot here, right? To operate the process inside a production line. Okay, so let me, in the old day, you will see we have a lot of human worker, but here you do not see that. But when you see picture like this, obviously all these production are being operated by human worker, right? But in today's situation, now you see opportunity for you to deploy your robotic arm to do that something, etc. Right? Okay, and you can use robotic arm to operate the welding process. Okay, this is a welding. Okay, but here you see you can either hire a human worker to do the welding or use robot to do the welding, etc. Right? That is a process which occur at each station. But since we have a series of stations, pay attention to this need for transport. Okay, so output from station one will be the input to station two. Then you need to have equipment system which do these kinds of transportation of material inside the production line. Then here you see the typical scenario. Either you use production line or conveyor. Conveyor is this one section of the conveyor. Or use AGV, right? Now you see mobile robot, you put the deploy your mobile robot. Or autonomous vehicle, right? This is a Ford machine, right? So this is a vehicle, right? Okay, these are three typical solutions for us to achieve the need for transport. Okay, so based on the previous slide, we highlight to you the basic scenario in the production line. Then we can try to come up with some key parameters, right, which will dictate the efficiency for you to operate the production line. Okay, first parameter is the service time per worker. Let's say in the production line, you hire only 5 people to do the same operation, right? But you know, okay, different individual has a different capability. Like you cannot say all of them are identical in terms of physical capability. It's impossible, right? You see, this guy may take 2.5 minutes. This guy faster 2.2. And this person, I do not know why, what reason that he will take 2.6 minutes to finish the same job, right? Then in this case, because for for the study, so for to facilitate the theoretical study, we always consider worst case scenario, remember, right? Then for this process, for this mining process, service time per worker should be 2.6, right? Also, this one can finish earlier, then he can take a rest. Understand? We always say the worst case scenario. Service time per worker always choose the time taken by the slowest worker, 2.6 max, right? Okay, we just for you to know. Okay, this is the manual production line, right? If we talk about the service time per worker in this production line, always identify the slowest one and they use the time as a measurement, okay, or as a value for theoretical study, okay. If let's say you have a machine, but sometimes you may buy machine, this three machine from company A, this guy from company B, this come from company C, this come from company B. So different company will produce same machine with different capability, right? Same situation, right? So service time you always consider worst case scenario, right? Among all these machine may do the same thing, but they are the product of a different company, right? So their performance can be different, right? So then always think use a worst case scenario to treat as a service time workstation, right? But here you see all these robot looks like the same. But eventually, some robot come from company A, this robot come from company B. There is a slight difference, right? There, okay. So then we always use a worst case scenario to measure service time workstation, something like that. Okay. Then repositioning time, but this is the standard terminology used in manufacturing. So it means for one workstation to be very easier to take in the input, this is time spent. For example, the output from station 1 become an input of station 2. But it takes time for the output from station 1 to reach input of station 2. All these are counted as a repositioning time, right? But you see, from 1 to 2, you take a certain amount of time, 2 to 3, maybe another amount of time, 3 to 4, etc. Then we always consider worst case scenario, right? Compute the maximum time taken by any pair of two adjacent workstation, right? Then we use this value as a repositioning time. Always consider worst case scenario, right? So these are the basic parameters, right? So here you see you have a two robot. Eventually, their performance value cannot be exactly set. This is one thing from a different part, another thing now you see this guy, this out here, you see this out this one, right? And also whether you see or not. Okay, then to this one. Like you say, we saw this one. This is a lot, right? Yeah. Just for you to know. See. Now this equation is very, very interesting now, right? So this equation is for you in case in future you become a CEO of a company or you become a manager of a production line or factory. Then you must know this equation, right? So that means we need to determine production time, unit product, right? This could be dictated by the inner capability of your production line or dictated by the marketing and the sales department. For example, in your company, marketing and sales department say I can sell 1 million cars per year. Then if ask you, if you are the manager of the factory, are you able to produce 1 million of a car per year or not? Right? If you cannot, then you must meet this requirement. right? If let's say you can produce 2 million of car per year, but the marketing and sales department can only sell 1 million. It is also a problem, you have overcapacity, you waste money of the company, right? Because the CEO will say, why you purchase so many equipment there? Why you hire so many workers because you can produce 2 million car per year? But however, we can only sell 1 million per year. Understand what I'm talking about? Or reversely say, our sales marketing department can sell 1 million a year, they can only produce 500,000 per year. All right, then you must set up a more production line, hire more workers. That's it, right? So you see, these are the data very important for CEO to know. Okay, so you see, this is kind of easier. Number of weeks per year, by 52, minus some holiday, right? And number of shift per week, normally it's 1, some is 2, or sometimes maximum 3, 3 times 8 is 24, right? So either 1 shift per week or 3 shifts, right? And the operation hour per shift, standard value, according to international law, 8 hours per shift, right? Is law. Okay. Annual demand for a product. This is the data from marketing and the sales department, right? PA, marketing and the sales department. If this data dictated by marketing and sales department, you say, I can sell this amount of product to the market. All this data is dictated by the production line. You say, I can only produce 1 million a year, then you just sell 1 million, right? Even you can sell 2 million, but don't tell the boss sell too much. Understand? Okay, so then as a CEO, you must use this tool. Okay, PA may equal to this, may equal to this, depends on your focus. Either you focus on the marketing and sales, right? Or you focus on the production. Yeah. So based on this data, then you can determine to produce 1 unit of a product, you only allow the time. Just now in the video, have you paid attention for that production line? In 1 minute, how many cars can produce by 4? Do you remember? Is it 16? 16 car. You know this number, 16 car per 16 seconds. 16 seconds is 1 minute, right? 1 minute produce 16 car, right? Okay, so that is the production capability. Then you can ask this question for your marketing and sales department. Can you sell 16 cars per minute? That is quite hard. But if let's say you have an international network, it should be easier, right? 16 cars per minute. Okay, understand? So that is the average time resources, okay, for the production of each unit of the product. Okay, then, but the thing is, if let's say if you constrain the time so tightly, if a little bit of variation, then you will miss out the target, right? So this is why they come out this terminology. This one is more or less a production plan dictated by the sales department. Normally dictated by sales department. This one dictated by the factory cycle time per unit product, right? So dictated by the factory. Then normally we want this time, you see cycle time, production time to be equal. Then this V equal to 1. Or we want this guy slightly greater than this one. So that means this year is close to 100%. We should not overshoot. If overshoot means what? Overshoot means you need more time. You cannot meet the sales target. The sales department says you can only produce 1 car per minute, but you need 2 minutes to produce 1 car. That means overshoot the inner capability of production, right? So normally this E we call efficiency of production line should be close to 100%. Exceed 100% means what? You cannot meet the target of the sales. If it's too below 100%, means what? You waste resources. A lot of workers just sitting there doing nothing, right? Yeah. So this is minimum, right? So this is your actual capability to produce a car. This is a capability for your sales, marketing and sales department to sell a car, right? So you must match this two, okay? Maybe this guy to be close to 100%, right? Next school, maybe 95%, 99 or 93. Understand? Okay, but as a CEO, you just monitor this data, you know what is the situation in your company, right? Okay, yeah. And in case, okay, once you know this, if you are the manager of a factory based on this data, but eventually this could be top-down data. If let's say your marketing sales department, based on the capability of sales, you know, okay, you say to produce one car, you can only have 1 hour, right? Then your CEO say this guy has to be 0.95. Okay, dictated by your CEO. Then 0.91 times this, then you get this number. Based on this number, you are the manager of the production line. Then you need to know how many workers to hire, how many machines to purchase, understand the thinking, right? So let's say minimum number of a workstation or minimum number of a robot to purchase. This is to finish a car. What is the actual time you need to spend? Maybe to produce a car, you need to have 10 hours, for example. But if you have 10 machines work on the car, each machine just spend 1 hour. Understand? Okay. So based on that, we can determine number of workstation. Each workstation contribute this amount of time, so that this number times this number greater than this is the work content time, the time needed for the completion of a car or vehicle. Okay, so okay, get used to this thinking. All this thinking mathematically is quite simple, not complicated. You just get used to this kind of thinking. But all this thinking is for you to behave like a manager or CEO, etc. Right? So let me just summarize the information from previous slide. Okay, work content time. This is produce a car, you need 20 hours, right? And then you have a lot of work, use many worker to produce this car, right? Service time per worker. Always remember this is worst case scenario, right? Reposition time means the car or the unfinished part go from one worker to another worker. We will take time, right? Always consider worst case scenario. Then the cycle time per worker is this one, because the worker will take service time this amount, repositioning time this amount, added together is a cycle time, right? So this you cannot. This is a fixed cycle time. Then number of a worker deployed. Then this guy you have this. Then you have this number of worker to hire, etc. Okay. So with this number of worker, this guy, because this is the integer part, then this one times this one, this is the actual service time, the total amount of service time, TS times the W. Total amount of service time normally is greater than the time needed by the production of a product. But this also, as a manager, is another indicator to see whether you have maximized the use of a worker or not. If this guy is very low, not close to 100%, that means your worker actually has a lot of rest time. Finish the work, then spend a lot of time just doing nothing, right? Yeah, okay. So it's good for you to know the thinking of a manager, thinking of a CEO. Okay, this is treated as a homework. You go through all this, then you will know. Okay, in future, if you work as a manager, work as a CEO, and automatically you know what should be the mindset of a CEO manager. Yeah. But if you work as an engineer, you don't care about this. This is not worry about engineer or worker don't care, right? Pay attention. If in future you become a boss of a company or you set up your own company, This is a must, right? Otherwise, your company, your corruption, or you're going to bankrupt, close down, you lose money, right? Here. So now you see, it's not easier to be a CEO, right? To be a boss of a company or to be a manager of production line. Okay, now you know how to become a good CEO or manager in the production line. Clear? Okay. So previous scenario is about the hiring of a worker. Then how's about the deployment of a robot in the production line? Now we talk about the service time of a robot, right? Workstation in the automated machine. But here we think about the robot, right? And the same law, because robot, at each station you have one robot. Then if you have a many station, you have a many robot, right? And then you also need to take time to transport output from one robot to become an input to another robot. You see, okay. But here you need to pay attention now. But it's very strange for the worker. We never consider the medical leave. You know, worker can ask for leave, fall into sick. Okay, maybe once you have a worker fall into sick, we can easily hire a temporary worker, easier or ask your friend just replace, right? So that's not cost too much, right? But once you have an expensive machine, robot is difficult, you cannot buy a new one standby there, right? So when your robot has an issue or your robot breaks down, right? You see the downtime. Then you must consider how long will take for you to do the repair. This is a repair time when the robot breaks down. Then this is the probability for your robot breakdown. So you must do the big data analysis. You can predict what is the chance for each robot to break down on annual basis. All this can compute what is the probability. If you have many robots, then all this probability together, right? Then the breakdown, this is the downtime times the probability, the sum of the probability. Then this you must keep some allowance to handle repair of the machine. Then your production line actually is equal to the cycle time of the workstation. AE is the extra time which corresponds to the repair, right? So that is a production time for that, right? Okay, so this gives you little bit allowance, right? Okay, then from here, then you can talk about the line efficiency. This is assume that all your robot in the working condition, right? Then this is the cycle time. Once you consider the downtime, because once your machine break down, you cannot buy new one, expensive. Assume one robot 1 million or a few 100,000. Okay, so you just do the repair section. Okay, then you see you can get the efficiency. You see this guy always better than TC. Give some allowance, right? But here you have the same scenario. Okay, to produce a car, you need this amount of time. Each robot can only contribute this amount of time. How many robots do you need to deploy in the production? Right? Yeah. Okay. So yeah, then if let's say this guy is you cannot match with this, make this guy to be closer to 100%, right? If you do not have a sufficient number of workstation there, you can increase this number, right, in order to meet the requirement of production time, etc. I guess we go through the exercise and you will know, okay, how to use all these simple relationship, right, to compute the information needed for you to know. Okay, so you go through, treat this as a homework, then roughly you will know what the thinking of CEO, etc. Right? Okay, so that's about some mathematics involved inside the production line. Okay, then little bit of detail about the input material. I guess we can skip this one because you need to spend at least one semester to study engineering material. Okay, so you just quickly know. Okay, so at the material level, if you go down, you have a molecule. Inside the molecule, you have an atom, right? So you have a hierarchical structure among the atom and the molecule. Okay, so relationship between two adjacent molecule or atom. Okay, so and between two adjacent molecule, then they form these kinds of bonding, right? So they have interaction force, okay, or attractive force. Then based on this basic relationship between any pair of two adjacent molecules, then if you have a lot, then you will form this kind of structure. Okay, and these are the typical configuration among the molecule, among the atom, which will form a molecule, etc. Okay, so each node is an atom, then you see the relationship, okay, or configuration inside molecule. Molecule we call it as one cell, right? So you have these are three typical type of structure of a cell, right? And then all the cell can form another type of structure, so crystalline, etc. Right? And these are the typical example for you to have this body centric cubic, phase centric cubic, hexagonal closed packed cell, etc. Right? Okay, and then all the cell will form the structure of the material, right? So these are the typical structure, okay, among the cell, right? And this also help you to understand how come we can change the geometry of the materials because the cell will undergo displacement internally, right? And the deformation. This is just for you to know, okay, how come we can change the geometry, right? And for metal or regular material, you have these kinds of inner structure among the molecule, and then you may have a molecule in these kinds of configuration, right? Okay, etc. And this is for you to know how come we can change the inner structure of a cell, and this is because of you see when you apply external force. And these are the terminology of stress means the applied force divided by the section area, right? So you can say this is similar to the pressure. It's a force per unit surface, right? Force per unit surface, right? And the strain means you apply a force which will cause deformation, right? So I guess I can skip this module, but it takes time. Because we may not have enough time to cover this. And this just for you to know elastic material and the non-elastic material. You look at the relationship between strain and stress. If these two parameters form this linear relationship, that is elastic material. If they do not follow linear relationship, then that is non-elastic material. Sometimes we may not have this, we may not wish to have this property. For example, when you bend a material, if the material has an elastic property, then it will sway back, right? So maybe operation difficult, right, etc. Okay, so this just for you to know. You see, our ancestor and in the old day, okay, has this desire or curiosity of making use of a material to produce desired geometry for any specific purpose, right? So you see, in terms of material, it doesn't change, but the geometry of the material give you a different appearance. This is why think in terms of the geometry of the material, right? So when you do the manufacturing, normally we do not change, right, the property of the material. Okay, but pay attention when we talk about the manufacturing. By default, we talk about the mechanical manufacturing. In parallel, we have a chemical manufacturing, biological manufacturing. When you talk about the chemical manufacturing, then the purpose is not to change the geometry. The purpose is what? To change the material itself. There's a chemical reaction, then you produce a new type of material, yes or no? That is a chemical manufacturing. Here, like before, we talk about the mechanical manufacturing. Then we only change the geometry of the material. We never change the inner property of the material. Okay, yeah. So then how to change the geometry of the material? These are the typical process. Pay attention. All these are the process which allow us to change the geometry of the material, right? So, strictly speaking, this corresponds to mechanical manufacturing, right? Remember. But on top of this guy, we have a chemical manufacturing, biological manufacturing. Okay, they are totally different. Okay, how to facilitate the change of geometry? I guess all of you know, right? The easiest way to change geometry is when material in the state of gas or in the state of liquid. But the drawback is what? But in the state of the gas, when you change the geometry, the material cannot remain at the desired geometry, right? After a while, you can change that, right? So normally it's what we play between these two, right? Or increase the temperature of solid so that the solid has tendency to become a liquid. Then it's easier for us to change the geometry. So based on this slide, we understand, okay, control of the temperature will help us to change the geometry of the thing, right? Okay, so this is a typical scenario, right? For us to, okay, transform input material in the form of liquid into output material with any specific geometry, right? And in the state of solid. Now this is the output. This is input, this is the output. So this is very old simple process, right? And the sintering is another process. Okay, input is a solid in the powder. Then we apply the force. We also apply the change the temperature. Then this is the output in the solid, but in the specific geometry, desired geometry. So look at the geometry, they are different, right? Again, input, okay, and then output with a specific geometry of these two types. You see, force control, temperature control. Here also, this is the input, then this is the output. You see the geometry has been changed. So conceptually, it's quite easier to understand. Okay, this is the machining process. Input is very big cylinder. Then output, we remove the material layer by layer, then become this different geometry, right? This is the input, then we remove a material, then we drill a hole, right? Then we remove layer material, layer by layer, right? So again, it's a change of geometry, right? Very simple, okay? So this is just for you, okay, to practice, okay? Whatever we have gone through in the previous slide, second home question, but solution I given to you, right? So this is about the first lecture in session 2. Maybe we continue, right? I quickly go through this one, then we take a short break, right? Okay, now we spend more time to look at the process. So part 1 basically give you a quick overview about the manufacturing system, production system, input, output, inner process, and some theory, some mathematics about the way for manager, for CEO, for the boss of a company to manage the production line, right? As a boss of a company, you must have a minimum level of knowledge, right? And based on previous slide, now you understand. In China, we have many CEO only with primary school degree, yes or no? Now I understand how come can we make China to be an advanced country? You know, all these sports they only have a secondary school degree, yes or no? If you tell them all these equations, I guess they will die. Okay, so it means what? In future, I hope try not to become an engineer, right? Why do you want to become an engineer? Why not become CEO? Right? So that should be your mission. Understand? replace all the CEO, existing CEO in China, only people with primary school degree, right? Otherwise, you will suffer as an engineer, then your boss know nothing, right? And manage the company in a very bad way, then you suffer. Okay, so previous part one is for you to know what should be your mission in the future, right? Try to become a CEO, educated CEO, right, or manager, right? Clear? Okay. Now we zoom in into the process. Purpose is to identify the key variable, key parameter for us to put them into control, right? Because when you design control system, you need to know what to control, right? Otherwise, why do we need to design a control system, right? So at least you know, okay, what are the motion to be put under control? What should the temperature to put under control? What should be the force to be put under control? What should be the pressure, etc. Right? Clear? This is the purpose for you to go through part two, so that you can identify opportunity for you to implement automation system or control system. All right. So I just quickly go through. So I just use these two popular type of process for you to identify key parameter to be under control. Okay. So testing process, you look at this video. Implement here. In the liquid state, then we put down the material become solid with desired output geometry. And done again. Okay. Then you repeat the mass produce identical part. Okay. Now you understand how to achieve a mass production of part. Okay. Then one more. Previous one is expensive when you design the die, but this is a very, very cheap way. Sand is cost nothing, right? So you have a prototype part. You use prototype part to form the geometry of the inner cavity of this die, the sand die. Okay, we call this a die module, right? Okay. Then you turn over, remove the jumper part. Then you see the cavity with the specific geometry. All right, so you see you have a cavity geometry. You must also provide the circuit for you to pull the liquid. The liquid will follow the channel, the tunnel, you can say tunnel, so that it can flow inside the cavity, inside the die. Then when the temperature go down, then you see the solid appear, right? Then solid means the desired geometry, right? So you see this is the produced part. Okay, clear? Then it's one more. Okay, I guess we can skip this part. Similar to the previous one, one way. We use the download product to give the inner cavity inside right? Okay, simply the cavity inside the die. They pull in material in the form of liquid, put on and make the material solidified, right? Then we have the output material, we the diameter, right? Okay, so conceptually very simple, right? So then this summarize the task, okay, to mass produce identical part with the desired geometry as an output. Then our focus now is action to operate on this process. Okay, we summarize the action. Then for each action, we need to know what are the critical parameters to be put under control. Now you see temperature important, yes or no? Motion is important. Timing is also important, right? And when you remove the mode, force is important, right? And the inspection for quality control, appearance of a finished part is important. Then you see these are the opportunity for us to automate this process, for us to implement, automate or control system. Now this is a feedback control system, right? This help you already. Okay, then some more illustration for you to see this type of process, etc. Right? Okay, and okay, this is just for you to know when you do this kinds of process on Earth, we have a gravity, yes or no? Once you put the liquid inside, due to the gravity, then density at the bottom of this finished part should be higher, yes or no? Due to gravitational force. How to overcome this one? You may heard of we may set up the factory in the outer space. Now you see advantage you have a factory in the outer space as well. Then we can overcome this one. Or on Earth, how to overcome this? Then we must artificially produce centrifugal acceleration now, which should be 60, 80 times of a gravitational acceleration now. Then you can produce a part with uniform density. In case if your machine require such uniformity in terms of density, right? So then you see the cost of production will be high, right? Unless you go to outer space, right? Okay, but these are simple physics that you can easily go through, right? So then what is this is the angular velocity or circular velocity. Then what should be this one is what? This is the centrifugal acceleration, centrifugal acceleration, right? Yeah. So then you follow this by this nearby physics, you can easily go through. Okay. Another process is injection molding. Then you look at this video, right? This is also a way to mass produce part. Input solid in the form of tiny particle. These are the heater transform solid into liquid. You see the heater, right? Solid, then inside the liquid engine into the chamber. Then you solidify that again. Then you have a spool, right? So this side solid, this side liquid. Inject into the chamber. Chamber on the back is I see chamber inside. So this is the material in the state of solid or liquid. They put it down and solid and so you can mass repeat or mass produce. Okay. So then this is the task of summarize what you have seen, right? Then you see the action, how to operate this injection molding machine. So this summarizes the sequence of action. But for us, we need to know, okay, how to automate the key parameter. Okay, so this helps you to understand all this action, right? So you have a chamber inside the die, then you inject the liquid into the chamber, cool it down, solidify, then remove the die, then you get the solid as output, right? So you see motion control important force, because when you inject, there's a force there. Temperature control, you see motion, force, temperature, timing. Okay, so there are a lot of opportunity for you to do automation inside this process, etc. Right? This is some extra knowledge for you to know, because you know, okay, for material, they have this coefficient of expansion. Okay, they can expand in 1 dimension, 2 dimension, 3 dimension, right? When you cool it down, then have the shrinkage, right? Expansion or shrinkage. This is why you need to provide some extra material, okay, in order to prevent the deviation of the geometry from the design specification. This is just a background knowledge for you to know, right? Okay, so this also help you to see another way to transform input material in the form of a powder or particle, and the output material with a specific geometry, etc. Right? Sintering is similar to the 3D printing. This is another way to transform input material in the form of a powder, then output material in the form of a specific geometry. Right? In this case, it looks like here, right? Input the powder through the application of the form. Then you get the field. The output material is the geometry of the field, right? Okay, then if you keep the part produce this type of mechanical part, right? Okay, so good enough. Then one more example. And this one you could either to solidify the powder layer.
Direct metal laser system, also known as
All the technology
creates metal parts directly.
but actually it's look like a street.
DMLS utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and aluminum, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes, high temperature applications, and end-use parts. DMLS concepts begin in the same fashion as other layer-active manufacturing technologies. A program takes 3D printing. Each of these sections will act as a defect found in the DMLS machine exactly where it's suited the metal material. Data is then transferred to the DMLS equipment.
One day of let's use the laser. Solidify how is liquid. So this looks like
Once the layer is completed, the base plate is lowered. So
let's say you see the paper go down layer by layer. Right? Right? Get the
DMLS machine is used to single layer on layer. As the part of the force running back to the subcontractor credit, find features of no remaining services.
okay, it should be good enough for you to understand. Okay, then we have some slides help you to know how to produce powder of metal, because you see our metal is very hard, very rigid. How to produce metal powder, and this slide help you to understand we are able to produce metal powder. Then use metal powder, then you can print any metal object through the sintering process. Okay, so this is a class description. So you will see we print layer by layer, right? Use the metal powder, right? So it's very important. Then okay, we have two videos. First video is use the pressure. We have a bunch as a die. Then you see the action. Second one is very much looks like a 3D printing, right? By before 3D printing use a polymer, but here you see use metal powder, right? Okay, and the focus for us to identify key parameter for us to control. You see, motion is there, temperature, force, motion, force, motion, timing, right? So you see, motion appear everywhere. Now you see, motion is very important. Physical quantity to be put into control, right? Okay. Then one more illustration. This also help you to understand through the application of a force, we can also transform input material into output material of a specific geometry, right? And this illustrates the printing process. But here we call sintering. You see the motion control of this table, okay, control the z coordinate, then layer by layer it goes down, right? Then the metal part appear, okay, it looks like this, okay, here. And another one is deformation process on the automation. So rolling is a typical one, right? So then you look at the video, then you will see how to, okay, increase the temperature of the material, but the material still remain in the solid state. Then we modify it.
So, and for that reason, it is generally rolled once it's hot. To make sure the steel is the correct temperature for rolling, it is fed to a furnace. Here it travels through several temperature control zones until it's at the correct temperature and ready for rolling. Whatever the product, the principle of hot rolling are the same. Steel is squeezed between rolls until the final thickness and shape are achieved. To do this, the rolls must exert forces of tens of millions of newtons, equivalent to a weight of gravity its times. The rolls, therefore, run in massive bearings, mounted in housing of enormous strength and driven by powerful electric motors. These are known as millstones. The layout of a rolling mill can vary from a simple single-stand mill to several stands positioned either side by side or in a line. The mill rolls themselves can either be plain for flat products such as strip, used for products such as cladding, or profile for sections, beams, and columns for use in construction. Mill stands have various arrangements depending on the product being rolled. The simplest arrangement is a two-high stand, used mainly for long products such as sections. For light sections and bars, three-high stands are sometimes used, with the steel passing one way through the bottom gap and back through the top gap. Four-high stands have two work rolls in contact with the steel, supported by larger backup rolls to prevent slippage caused by the rolling face. These give greater accuracy for rolling fat products, such as plates. Universal beam mills include stands with both horizontal and vertical rolls, then on steel simultaneously. The rolled steel is then cooled in a way appropriate to its end use and prepared for further processing or dispatch.
Okay, this should be good enough for you to know, right? The hot rolling, right? But hot rolling has a drawback is what? When the temperature goes down to the room temperature, there's a shrinkage, then there's a geometry change again, right? So for high precision manipulation of the geometry, try to use a cold rolling, but cold rolling is very hard to operate, but quality is high, right?
Shape has been innovating in this field of rolling for over 40 years. Among many events, Shape has developed three distinct processes for MRC. First, in one direction, then in two, and now in three directions. With this technology, multiple parts can be manufactured with only one set of tools. Traditionally, would require a separate tool for each part. With the high strength steel sheet, the roll forming process starts at the core.
With the input material. You can consider it the other linear process. Welding or cutting, right? So you cut in, but it will also go standing to the standing remove, right? Then go to all the roller, use on the roller, right? Then change the geometry of the shape, right?
The roll functionally creates the cross section.
And you see that geometry start to form, right? The width change, right? Then you see that how this is the welding of joint of the then go to rolling again. Now you see this is the output of time. This is the one dimension. Put another pair, another dimension. Because this group they also change. Okay, so it should be good enough for you to know. Then this summarize, use a roller, you can modify geometry of the input material, very simple, right? Then hot rolling, these are the actually cold rolling, simple, right? But drawback of this one is you cannot achieve a very accurate geometry change, but this one you can achieve a very accurate output geometry, right? Then you see for hot rolling, control of temperature, motion, force. For this one, there's no need to have a temperature control, just motion force. Okay, very simple, right? And there are some mathematics. Basically, it's showing you the conservation of rolling, conservation of material flow. Then, based on this information, you can, if you know some related parameter, you can determine the rest, right? So this is a simple mathematics involved in this rolling process, right? You can also use two pair of a roller work together, increase the diameter. If let's say, if you control the relative distance between these two pair of a roller, then the diameter of the ring will increase by extension, right? This is another this is a very old process, right? For change to change the geometry. I guess all of you know this process. We can manually do this kind of in ancient China, we use the process to use a lot of metal tools. But today we use a machine.
Which deform the workpiece to control high pressures.
Don't think it's a manual way. That's all we know.
It's 8,000 BC. It is utilized today to reduce the cross section, improve the metallurgical microstructure, provide directional grain flow, and eliminate porosity of gas ingot in fabricating rock mill forms, and to form discrete parts to near net shape from these rock mill forms, further refining microstructure and directional grain flow. Because of these effects on microstructure and grain flow, the mechanical performance of rock mill forms and parts is typically superior to that of cast metals. Open die forging is performed on ingot, billet, bar, or a preform, and is the deformation of a workpiece between flat or shaped dies without completely restricting metal flow. This deformation can result in lengthening of the workpiece while reducing its cross section. Upsetting regions along the length to greater sizes than adjacent regions.
See the change of
Bulging the workpiece's cross section while reducing its length. Lengthening and offset are typically done using forward effects as the workpiece is incrementally advanced lengthwise and rotated on its longitudinal axis. There is essentially no limit to the size of forgings that can be made using open die forging. They can range from a few centimeters to 30 meters in length and weigh from a few to up to several 100,000 kilograms.
okay, it should be good enough for you to know, okay, through this forging process, we can also change the geometry of the input material into the desired output geometry, right? Then look at the action, impact, okay, then it's like gradient pressure, etc. But our focus is look at the temperature control, motion control, and force control, etc. Right? So all these are the opportunity for us to do automation, right? So that is the illustration for you to understand what is the open die fortune, impression die fortune, right? And flashless fortune, etc. These are some specific process, okay, which are related to fortune. Extrusion is also a very popular process in industry, right?
The primary design of products
So it's the input.
or forward extrusion. In direct extrusion, the hot billet is loaded into a thick wall container and forced through an extrusion die secured in a hole. The force for extruding is applied by a ram, along with an intermediate reusable dummy block. Metal flow from the die is in the same direction as the forward motion of the ram. Since the surface of the billet length slides along the wall of the container, extrusion force depends on the friction between the billet length and the container and the material. The friction portion of the force can be reduced by using lubrication. Force increases
You see the opening of there is the output,
then increases
output material, okay, the
force before extrusion begins.
and force.
Upon breakthrough, the force declines as billet length decreases until a minimum force is reached. As the billet bends, the force rapidly rises again to continue metal flow radially toward the die. Resistance to deformation
Okay, so going up, you just know, right? Okay.
is a
The material could be no metal material, right? So this is illustration and action. And then you see force control is very important, the motion force, then flow velocity, magnetic control velocity, etc. Right? So some more illustration for you to understand this extrusion. Bending is another process once you change the geometry, right? So then.
So you want to give you a little insight into what we did here at Children Pro. We're going to show you some clips of the work we do at our facility in Sydney, Ohio.
So you see this the typical
Then it's not
process in bending.
Bending is a manufacturing process that produces a U-shape, or channel shape along the straight axis in sheet metal. Children Pro uses manual, semi-manual, and even fully automated press brakes. The press brake works by applying many tons of force to the workpiece. The part is positioned between the punch and the top. The punch is a piece of tool steel terminated in a place that press the workpiece is therefore
Right?
There are many
Okay, just before you start, just okay. This one, I just maybe the thing the set and eight. Right? So you see bending also here. We can produce a very complicated change of and another slide. Okay, before you that, so you already know how to change the geometry of a metal sheet, right? So then you see the illustration here. Then based on the V bending, H bending, then the action will be slightly different, right? But for us, we just look at the motion control, force also involved, right? Because there's an action force there. So motion force, right? Quite straightforward. And just like I mentioned, if the material has the elasticity, because after the process, once you remove the die punch, then this is a spring back effect, right? So this is a spring back effect for us to know, right? So this will will affect the accuracy of a geometry to be changed, right? Okay, so eventually we also create this zigzag shape or circular shape, etc. Right? And this also belong to the bending process, etc. Right? Okay, then for this part 2, there are some exercise for you to go through because solution has been provided. So this is just for you to digest, okay, the mathematics involved in part 2, right? So you go through, then roughly you know, right, the knowledge, background knowledge involved in the part 2. Maybe we take a break of 5 or 10 minutes, okay? We start at 4 o'clock, okay? We'll take a short break of 10 minutes. Okay, so we continue with the study of part 3 in session 2. Okay, by now we understand that the manufacturing system include design, production, marketing, and the sales, right? So design will provide the input of a part join to production system, right? Production system will also take engineering material as an input. By default, manufacturing here means mechanical manufacturing, right? So we are not talking about the chemical manufacturing. We are not talking about the biological manufacturing, right? And inside production system, we have an input, we have an output, we have an inner process which transform geometry of an input into desired geometry as the output, right? And the last activity inside production system should be assembly, right? So you have seen the video in which the assembly could be done by a single person or by a group of person in the production line, right? And we have also studied some difficult process involved inside the production system, right? And among those difficult process, we are able to identify the key parameter, key variable, which must be put into control, right? So by controlling all these key parameter or key variable, we can achieve the desired output in the production system. Okay. Now the big question will be: are we going to make use of human worker, to manually control these key parameter or key variable, or are we going to deploy machine or control system to achieve the control of all these key parameter or key variable, right? So obviously in today's situation, we must make use of control system to achieve automatic control of all these key parameter, right, or key variable. Then you may want to know, how are we going to design all these control system, right? So you remember in section 1, I asked you just to remember this 1, 2, 3, 4. Okay, 1 system, 2 output, 3 KPI, 4 means what? 4 design method for you to achieve the design of a control system. Okay, so part 3 will help you to study these 4 design methods, right? For our students, they are going to spend 1 semester to study these 4 design methods, right? But here you are going to spend 1 hour to quickly go through the key principle behind or key procedure behind these 4 design methods, right? Okay, so now we jump into the study of designing control system with the use of 4 design methods, right? Okay, here. And in order to save time, I just quickly give you an overview about the process because just now we have already gone through the process on the control in manufacturing. Then we spend a little bit of time about the modeling of the electric actuation system. Okay, this is just for you to know. There's a good news in today's production line. You will see there are a lot of need for the control of the motion, and also they are mainly need for the control of pressure, etc. And behind all this control system, you will see the presence of an actuator or electric motor. So as long as you know how to control electric motor, actually you should be able to fulfill the mission of implementing control system in today's production line, right? Okay, so we will use electric motor as an example because this is the most popular device inside the production system, right? And then you can link this one with subsequent 3 sessions. When we talk about the IoT, Internet of Things, one of the major devices should be motor or actuator, right? And then you see these 3 topics are linked together, right? Okay. Then we just quickly give you a revision about the one we have studied in part 2 of today's session. Okay. You see a lot of process, right? Okay. So these are the welding process. Then we know there are a lot of solidification process. Okay, just now in part 2, we have gone through some videos, some example, right? So this just remind you, okay? Then for deformation process in part 2, we have seen the video about the bending process. The bending process is a typical example of deformation process, right? And also the rolling process, forging, rolling, etc. Right? So this just remind you, right, about the manufacturing process. Material removal, I guess we did not see the video, but I basically is use a cutter and make the material undergo rotary motion, then you can remove the material layer by layer in some specific way, then you can produce the output or material, right? Then so when you remove the material, you see the control basically is a motion and the force, right? To summarize, in order to implement this type of a process, you need to know how to control motion, how to control force. That's it, right? Okay. Joining process, typical one should be welding, soldering, welding. I guess we did not see this video, but this should be quite popular process. So basically, we join 2 workpieces together by adding additional material in the liquid state, then they solidify. After solidification of additional material, then the 2 workpieces will permanently join together, right? Then for this process, basically, we need to control the timing, control the velocity, motion, right? So this is not very complicated process. Okay, so among all these typical process, you see, we always need to do the motion control. Then how to achieve the control of the motion? You need to have a hardware support. So important, the hardware device should be actuator or motor, right? So here we just focus on the property of electric motor, right? And when you look at the way for the design of robotic arm, you see in section 1, we talk about the mechanical system of the robot. We have a joint, right? So inside the joint, we will have a motor. Motor here, I use another terminology. We call it a torque joint because the output the power joint. You see, power joint is a motor. This is a speed reducer because it amplifies the torque. Then this is a link joint of the robotic arm. behind you see you have a sensor. This is why this slide also remind you about this statement, which is to say that a robot is a mini version of an IoT, right? So inside you have a lot of electric motor, right? And the electric motor is also useful for us to achieve motion control in any automated equipment which we are output controlling for motion, right? Then it is interesting for you to know that what is a motor, right? Motor actually is a typical mechatronic device because motor has an electric property plus mechanic property, right? But the connection is what we just consider simple relationship, right? Torque produced by the motor is proportional to the current which flow inside the circuit of coil. Okay, so motor has a rotor stator, right? There is an action force. Okay, but mathematically, if you look at the relationship among the voltage and current, voltage current basically represent electric energy, right? Then torque and the angular velocity represent mechanical energy. From the principle of energy conservation, it means what? V times I, ideally, V times I must equal to T times tau, or omega times tau, right? Conservation of energy. But if you go into more detail from the electronic side, you have total voltage equal to the voltage drop across the resistor, voltage drop across the coil, right? And plus voltage generated by a rotating loop inside the magnetic field. Because when it's rotated, it behaves like the electricity generator. It will produce voltage, right? So these 3A together must equal to the input voltage, right? So you see this is a parameter which represent mechanical energy already, right? Okay. Then in the mechanic side, just like I mentioned, very simple. Torque is proportional to the current, right? That's it. So this is the equation which links the electronic system of motor to the mechanical system of motor, right? So you write I as a function of power, you get this one. Then you compute derivative of this equation, then you have first order derivative of current equal proportional to the first derivative of torque. Good enough already. Okay. Now from this voltage equation, you replace the derivative of I by this expression, replace I by this one. Then you have a relationship between voltage and torque, right? Torque, and this is the angular velocity. So basically, you can call this as a mechatronic equation, because V is a parameter which represents energy in electric domain. Tau is a parameter which represents energy in mechanical domain, right? Then if we want to know how to handle such equation in time domain, right? But for those of you who have studied control theory, I do not know whether the textbook is showing you this slide or not. Okay, I just add in this slide. Okay, so this is very important. Okay, so Nicola just tell you that in order to understand the secret of the universe, you just need to know energy, frequency, vibration, right? And frequency means what? You need to jump into frequency domain, right? How to jump into frequency domain? Because in time domain, it's difficult for you to understand the relationship among these, right? Okay. Once we go to frequency domain, this becomes extremely simple, right? So good news to you is the Laplace transform allow us to transform relationship in time domain into relationship in frequency domain. Okay, so this is why you need to know what is a Laplace transform. So Laplace transform actually is an extension of a Fourier transform. Inside Fourier transform, we only have omega, only have a single variable, which is omega, angular velocity, right? Then we extend omega, j omega is here, right? By another real number, then we form a space. Pay attention, treat this guy as a vector. If you consider this is a number, then you will suffer, right? Okay. So with the use of S vector, then we can extend the Laplace transform, Fourier transform into Laplace transform. So this is the Laplace transform. Okay, but you may say, well, this is very complicated to use. Good news is, in practice, you do not need to use this rule equation. You just apply some rule, you can easily do the forward transformation, reverse transformation. Okay, and the additional result for the Laplace transform is for you to predict the initial value in time domain, final value in time domain, without coming back to time domain. I mean, so you still remain in frequency domain. You can predict initial value, predict final value, right? So this is an additional power of Laplace transform. Okay, so now I mentioned we just use a motor, electric motor as an example. Then you will see in frequency domain, the relationship is extremely simple, right? So this is a real case where you have a motor, have this payload. Payload has a moment of inertia, right? And frictional force, damping coefficient is given to you. Now we ask you to find out the ratio between output Laplace transform and the input Laplace transform, right? You will see this is very, very simple. If there is a torque is a constant, 100 Newton-meter, what will be the steady state value of velocity, right? Okay, very simple. So we apply Newton's second law of rotary motion. The motor will output torque. Torque will overcome the viscous friction, which is proportional to angular velocity. Remaining energy will contribute to angular acceleration by this moment of mass, right? So this is it's a variation of the Newton's second law, right? Here we focus on angular velocity, then this is omega, this is the omega dot, right? Because it's angular acceleration, right? You apply Laplace transform. First rule is when you see derivative in frequency domain is S. This is the Laplace transform of angular velocity. Then Laplace transform of angular velocity is the Laplace transform of torque. Now you compute the ratio between Laplace transform of output input. Now you see this is a relationship function in frequency domain. Very simple. Now you look at the previous equation, it's very complicated, right? This kind of relationship, right? So in frequency domain, very simple, right? It's a ratio between two polynomials, very, very simple, right? Now if we say the input torque is a constant, what should be the output of angular velocity? Then in frequency domain, when you see a constant 1 in time domain, in frequency domain is 1 over s. Since you have 100, there is 100 times 1 over s, right? Okay, for those of you who not know Laplace transform, you need to do self-study. Because to study Laplace transform, I guess you need to spend 1 semester. Okay, so you see the power of all these mathematical tools, right? So then output Laplace transform equal to transfer function times Laplace transform of the input. You do the partial fraction expansion, you can easily prove this multiplication equal to the sum of these two terms, right? Then you apply the rule, we can go back, come back to time domain. 1 over s in time domain is 1. This you consider is displaced version of 1 over s. So 1 over s in time domain is 1. You have a displacement plus 0.1. Consider this is a displacement. Then in time domain, you just add in exponential function of displacement vector times t, then negative 0.1. Right? Very simple. Then when t go to infinity, then you have a steady state response. Okay, when this guy go to infinity, this is a steady state response. This we call it transient response. Now you see these two. One system, two output. One is a transient response, this is steady state response. You see, this helps you to do a revision about this 1, 2, 3, 4. You remember this 1, 2, 3, 4. Good enough already, right? Okay. So this is the way for you to know how simple is the dynamics of motor And if you have a machine with many motor, they just put them together, right? Okay, so in the previous example, you already know the concept of transfer function. Okay, transfer function means a relationship function in time domain between input output, so which is just equal to the ratio between output Laplace transform and the input Laplace transform. Okay, and then you need to know that, okay, for every system you have an input output. Okay, this is another concept about the ideal dynamic system, right? So then these are the properties of ideal dynamic system. Okay, so then the recommendation of the Nikola Tesla is for you to jump into frequency domain, right? So you see relationship in frequency domain very simple. Output equal to relationship function times input, very simple. But in time domain is a convolution, very complicated. Okay, so based on the but here we define this guy as a transfer function. Okay, basically it's a ratio between output Laplace transform and the input Laplace transform. Okay, but with the use of a transfer function, you can easily describe the input-output relationship. For example, this person uses his hand carry flexible joystick, a stick to control 2 degree freedom of a joystick. This joystick control 2-finger hand. Control robot hand with 2 finger. Robot hand with 2 finger carry another flexible stick, right? Then this will carry a chalk. The chalk will write on the whiteboard or blackboard, right? If you want to know relationship between this output motion and the motion of the hand in time domain, then it's a big data, right? But in frequency domain, you see, you have all these transfer function and time them together, right? So this just help you to know. Okay. Another thing is with use of a transfer function, we can draw this signal diagram. You must consider this is a signal flow diagram. But this diagram does not exist in time domain, right? Pay attention that when you see diagram like this is a relationship in frequency domain, right? But this diagram has an equivalent transfer function. This is the first formula you need to remember in control theory, right? So output versus the input equal to the transfer function of a forward prompt. This one times this one divided by 1 minus loop transfer function. This is the first formula you need to remember, right? Okay. So then this is an example for you to know, all right? Forward prompt transfer function is G1. Loop transfer function is what? G1 times G2, pay attention, negative sign here, times negative 1. 1 minus negative 1 is plus, then you get this one, right? Here is the same, you see, 1 over G times this guy. This is the equivalent transfer function of this loop. Forward prompt G1, G2. Loop 1 is G1 times G2 times negative 1. 1 minus negative 1 is plus, right? Then you see these two are equivalent, right? Yeah, okay. So then that is a relationship function in frequency domain. With the use of a relationship function, we can visualize the signal flow of any dynamic system. This is not possible in time domain. And this diagram helps you to understand the statement by Nikola Tesla. In order to understand the secret of the universe, think in terms of frequency. Why? Because in frequency domain, you can draw the signal flow inside any system. This is not possible in time domain, right? Once we know the signal flow inside the system, then you know everything about the system. That's it, right? Here, okay? So this is an example of signal flow. I use this term, signal flow, it's easier for you to understand. But the terminology in computer theory is called block diagram. But block diagram does not carry physical meaning, all right? This is why a lot of students suffer from the study of control theory. Why you suffer? Because a lot of terminology which are meaningless, transfer function meaningless based on the wording, all right? Block diagram meaningless, right? Based on the wording. Actually, you should call it signal flow, that is meaningful, yes or no? Right? Relationship in frequency domain, this is meaningful, right? Clear? Okay, so if you use the correct terminology, you will enjoy the study. Okay, this just help you to understand, appreciate the power of signal flow. Okay, this is the signal flow of a very complicated system. All right, the beauty is what we can simplify this one into a single relationship function without solving any equation. Magic, right? Okay, so I just showing you the result. First, you can easily prove when you see the summation, this is summation, you can swap the relationship of amount of signal remain unchanged, right? So once you see these two adjacent the summation, you do the swap, this is equivalent, you can verify nothing changed among the relationship inside this system, among the signal inside the system. Okay. Once you swap, then you see this is not standard feedback control loop because there's a signal come out, right? Because this signal will appear here, this is upstream, this is downstream. You can let this module take the signal from here, right? So let this guy take signal from here. But if the signal here is x, signal here should be x times G2. Then if this guy takes signal from here, you must divide by G2 to recover input signal from this guy. So how to recover input signal to F1? You must divide G2. Then you can verify, okay, by doing this, the relationship among the signal remains the same, nothing changed. Now you see if you apply first formula in control theory, replace this one by equivalent transfer function of for one pounds divided by 1 minus rho. Okay, this is what this is parallel signal flow, one flow here, one flow here. Let us stay them together, like we have two flow in parallel, merge them together, right? Merge them together. Now you look at this loop. This is a standard loop. Replace it by use a formula. Okay, for work bounds transfer function divided by 1 minus loop transfer function. Right? I help you to write down for work bounds 1 minus loop. Simplify it, you get this one. Again, this is what another standard feedback control loop, right? Replace it by equivalent transfer function for work bounds 1 minus loop. Simplify it. Finally, you see, without solving any equation, you can reduce any complex system into a single module, which has an input, which has an output. You see the power of Laplace transform. Okay, now the most important result is a design method, right? So there are 4 basic design methods in control theory. With the use of these 4 design methods, they should be good enough for you to handle majority problem of doing design. Okay, but later you will see with the PID controller in the whole world, more than 85% of our control systems are based on the use of PID, right? And when you read the published paper, and a lot of the people doing control, still a lot of methods. All the methods are in the time domain. Okay, you may have heard of a robust control, patch infinity control, all these okay, this square, okay, minimization control, all in time domain, right? But if you apply Nikola Tesla's lemma, you see all these are meaningless, right? Okay, so this should be the standard for design solution. Okay, so this method not only apply to automation station, but also automation station, but also to robot. Then you see you can link today's study to session 1, and okay, actually you feel excited about the knowledge behind control system, knowledge behind the automation system, right? Okay, so why do we need to do control? Answer is what? We want to achieve these 3 KPI: stability, fast response, and accurate response, right? You remember what is the best system in the whole universe? Static system, right? Here. So first design method is for you to achieve stability, right? So we call Rawls-Hurwitz criteria. So you use the transfer function of system, okay? a control. This is a transfer function of the control system, right? So normally is in the form of a ratio between two polynomial. You just pay attention to the denominator. So you use the denominator coefficient to fill up this matrix, right? Look at the degree of the denominator, because for each term you have a one row. First term is the first row. Second term is second row. You see s power n minus 1, all the way to this guy is what s power 0, s power 0. So depending the number of term inside the denominator, you have a matrix with this number of row, right? So you use coefficient here to fill up the element of the first row, Sn row, Sn minus row. In a zigzag way, you see An minus 1, An minus 2, An minus 3, zigzag way. Then you apply this formula to fill up the remaining element. What is this formula? You just pick up a 4 value from a previous 2 rows. 2 of them always from the first column. Another 2 of them always come from the next column. And it's An minus 1 for this guy, then An minus 4, An minus 5. Then how to compute this one? Then you see in the diagonal way, An minus 1 times An minus 4 minus An times An minus 5, divided by An minus 1. Okay, always follow this formula, done already. Okay, so this is the first design method, very simple. And you can understand this method by going through example, right? This is the denominator equation of feedback control system, right? Then we want to know, verify whether this guy is stable or not, right? So then you see what you have coefficient 1, A32, AT, 100. How to determine this guy? Is A times 32 minus 1 times AT divided by A. What is this one? It's A times 100 minus 1 times 0 divided by A. What is this guy? 22 times 80 minus 8 times 100 divided by 22, etc. Right? So there's a rule. If the number of change of the sign is 0, then this system is stable. Otherwise, it's not stable. Very simple, right? So you can use this tool to verify whether the system designed by you or by anyone is stable or not. But okay, this is an unstable situation. You see how many change of the sign? Positive, negative, negative, positive, 2, right? So this system is not stable, right? Okay, but important thing is to use this method to design the control system. For example, in this case, what should be the value of a k which will make this control system to be stable, right? So you apply this method, okay? So you see all these coefficients, you fill up the Rouse array, right? In order for the system to be stable, you need to first one is positive, then this guy to be positive, positive, positive. Then you have these 3 conditions, right? For this one, positive case must greater than negative 1, k must be smaller than 1, k must be greater than negative 1 over 3. Then this is a condition. You choose the value of a k between 1, negative 1 over 3. Done already. System is stable. You see, very easier to achieve the design of a control system which will be stable, right? Okay. Okay, this is a try exercise. Let's say they ask you what happens if I choose a maximum allowable value for k equal to 1. Then you see even k equal to 1, you get the 0 here. Then you cannot evaluate this one because when you compute this guy, is 0 times 20 minus 2 times 0, then divide by 0, go to infinity, right? So when you reach this situation, this one, you use the previous rule as coefficient. That means this will form another polynomial. This is the auxiliary polynomial. Auxiliary polynomial is part of the polynomial. It means you can compute the root of this polynomial. This root of polynomial is also the root of the original polynomial equation. But useful thing is you use this auxiliary polynomial to compute first order derivative. Then you use the coefficient of first order derivative to replace 0, 0. 4, 0, replace 0, 0, then you can continue to compute this one. Okay, so then for this system is stable, right? So this just help you to know this first method, right? Second method is to use a standard response or second order dynamic system, right? because you may always want to know what should be the standard dynamic system. Answer is this is the standard dynamic system. What do we mean by standard dynamic system? That means that any dynamic system could be represented or approximate by this type, right? And the inside you only have a 2 parameter term, omega n and zeta. But you rewrite this just simple mathematics, you can write in this way. You immediately understand, depends on the zeta's value, then you will know the property of the behavior. From here, you see, you transform this guy into here. One typical value for zeta is what? When zeta equal to 1. Because when zeta equal to 1, then this becomes 0, right? Another typical value is when zeta equal to negative. Negative, then this is a positive. Then you will see when zeta equal to negative, then this is not stable, right? So we do not consider when zeta becomes negative, right? So zeta could be equal to 0, value between 0, 1, equal to 1, or greater than 1, right? So this is the meaning of all these values are here. Omega n basically is this is the root of denominator. It is here. Distance from origin to the root is omega n, right? And the angle theta, you compute cosine theta, zeta is equal to cosine theta, right? What should be the best value for zeta? Answer is when theta equal to 45 degrees, then this guy equal to 0.7, right? Okay, best value for zeta is 0.7, this guy. Okay, clear. Then with the use of these 2 parameters, we can come out that design specification in time domain, maximum overshoot, time of the maximum overshoot, settling time with 2% of error, settling time with 5% of error. Okay, you can read the textbook about all this meaning of the design specification. But if you put yourself as a myself designer, you just remember it's good enough, right? So you see all these design specification is a function of omega n zeta. That's it. Okay. So then once you receive a design question, you will see the user will tell you, I want this system to achieve 5% overshoot, settling time is 2 seconds, error band is 2%. Immediately, then you know, right? Maximum overshoot is formula 5% equal to this one. You solve this equality, you can find the zeta 0.69, right? 2% error band, settling time 2 seconds. You apply this formula because you know zeta, you know this is settling time 2 seconds. Immediately, you know what is omega n. Once you know zeta, know omega n, you know this. You see, this is the design solution, very simple, right? So one more example, you see small k, capital K. We want the damping ratio zeta equal to 0.7, omega equal to 4. What should be the capital K, small k? Understand? First, replace this one by equivalent transfer function. Then replace this one by equivalent transfer function. Again, this one. Immediately you know capital K is what? Omega n squared. 2 plus capital K small k equal to 2 zeta omega n family, right? So K omega n squared. This guy 2 zeta omega n. And the question tell you omega n equal to 4, zeta equal to 0.7. Then immediately you know what is capital K small k. You see, this is the typical scenario of doing design with method 2. So method 2 allow you to achieve fast response and accurate response. Okay, and do you know the situation for this example? This example corresponds to what? You see, in this example, you can always find the value of existing parameter. This corresponds to what? Lucky situation term. Yes or no? You look at the question, you have a capital K, small k, just find out the value of this 2k, right? You are lucky, yes or no? And for this example, you are lucky, yes or no? You can find the right value of existing parameter down the D. Can you assume that you are always lucky in doing the design of a control system? Can you say that you're always lucky? Cannot. What to do if you are not lucky? That means no matter what value to choose inside the existing system, there's no way for you to achieve desired performance. Then what to do? That is the beauty of the control system. If you are not lucky, means what? You add in an extra transfer function here. Just add in extra transfer function. Understand? This is the philosophy. Then the question is, what to add in? What to add in? Answer is what? The number one choice in the whole world, PID. Number two choice is what? VLAC converter. That's it. So you see, with this four design method, we can handle majority problem in the design of a control system. No need to waste your time or do all those simple gaming activities. Okay, clear. So if you are not lucky, add in additional transfer function. Number one choice, PID. What do we mean by PID? Proportional integration derivatives. PID. That's it, right? So in the whole world, more than 85% of our controllers are based on the use of a PID controller. That's it, right? Here, if you know what is PID, done already, right? Okay, this example is for you to see power of a PID. Okay, here there's an additional concept about the MIMO I did not mention here. So you see how many input for this system? 2, 1, 2. How many output here? It's 2, they are superimposed together. Because this guy produces output here, this guy produces output at the same location, they are superimposed together. Still 2 output. So this we call multiple input, multiple output system. You must consider you have a 2 single input, single output system, 2 separate, right? Then your life is easier, right? This is background knowledge for you to know. Okay. So we first look at the relation. What is the output produced by this input? Then look at the output produced by this input separately, right? So you see, in your mind, this is the first SISO, single input, single output. Ignore this one, right? So then what is equivalent transfer function? Apply first formula control theory. The work from 1 minus loop transfer function. Simplify it, you get this one, right? If let's say you want to know relationship between error, this is the error term, right? Input minus the actual output, right? So this guy equal to what? This one equal to R minus CS, right? So this one divided by CS, because ES equal to RS divided minus CS, RS divided by RS1, CS divided by RS, this one. Replace this one by this one, then you simplify it get this one. Okay, this is for you to know you can compute relationship function between any pair of a signal, right? Okay, clear. Then you can compute steady state final value. What is final value of this error? Okay, apply final value theorem. S times Laplace transform of error. So it's a transfer function times the Laplace transform of input. Input is a unit one. So in frequency domain 1 over S. You do this evaluation and it turns out to be 2 over K. If let's say I can tolerate 10% of error, what should be this K? 10% error is what 0.1, then K will be 20. Very simple, this is that. Okay. Now I change my mind. Now you see the magic solution. Now I want the error to be 0. This is help you to know the magic power of the PID, right? Now you say I change my mind now, 10% too big. I want the error to be 0. What will be the solution? There's no way if the K is a constant. Now you see the magic of a PI controller. P means proportional, I means integration. You remember integration one? In frequency domain, when you see integration means you have 1 over S. This is the PI controller. Okay, add them together like this. Substitute this one with this one. Now you see this expression. Now you see magic result. Regardless the value of K1, K2, this is always 0. S equal to 0, always 0. Now you see the power of a PID. You can get the 0 error, Zero error means what? Output exactly equal to the input. Regardless what is the transfer function here. Now you see the QT, the power control system, right? Okay, so this is actually important. Then for second SISO, this is disturbances, whatever produced by disturbances in this error, yes, right? So you look at the transfer function, okay, for work rounds divided by 1 minus loop, like something like that. Then you look at the steady state output due to this guy, right? So when this guy is a unit step function, you see S times the transfer function. When the input, this guy is unit step 1 over S. Okay, simplifying, you get this one. How to make the output from disturbances to be zero? If this guy is a constant, no way. Now you see magic solution. If you use a PI controller, A them together, replace this one by this. Now you see magic result. With PI controller, regardless what is this guy will produce zero output in the output, right? So you see, now you understand the power of a PID. Okay, so remember a PID controller help you to achieve zero error, right? So you see 3 KPI, absolutely stable, zero response time. PID controller achieve zero response time. Then, zero error, 100% accurate. Response time you cannot be zero. Okay, you can make it as short as possible. Okay, and the previous example showing you, okay, method 2. You see, you have a design specification in time domain. You have at least 4, too many, John. Then you may want to know, because you know, in order to understand the secret in the universe, you need just think in terms of frequency. Then you want to know what should be the design specification in frequency domain, right? So the answer is what? Design specification in frequency domain is this position of the ruler, right? So just look at the location of the denominator. Okay, you remember when zeta equal to 0.7, you have a fast response. So as long as 0.7 means what? The root is in this direction of 135 degrees. So you choose the root in this line, along this line, then you have a fast response. Okay, how do I know whether I have a root in this line? You must draw all the possible ruler according to any design parameter. You plot out all the possible rule. This is this method. Then you see whether you have a one which is in this direction, 135 degrees. Okay, this is the design method 4, right? If you have, means you are lucky by finding the value of an existing parameter. What happens if you are not lucky? That means no matter how you choose this value, you can never find the ruler in this direction. If you are not lucky, same principle, A in additional transfer function. Then what to A in? Then in this case, just A in, be that compensator, right? Okay, very simple. Okay, but pay attention, design parameter could be anyone inside the denominator. But then you must rearrange it in this form, right? 1 plus the design parameter times something. So you can always transform this guy around this form. This is an example. K is here. Then you lump all this term which does not belong to K together. Both sides divided by this. You have a 1 plus K times this. Then this is the equivalent GS, right? Then K becomes design parameter, right? So, and how to draw the loop locus. In the old day, you must learn a lot of rule, manually draw. Today, you have a MATLAB, learning in fraction of a second, you can come out drawing of loop locus. You see, this is the key in GS, equivalent GS, right? So you use MATLAB, just key in, then you call the R locus, enter. I guess I do not know whether in China they give you free access or not. For NTU student, they have a free license to use MATLAB. Okay, so it's not an issue. So this just demonstrate to you how to use MATLAB to key in a transfer function GS, right? Okay, this is transfer function. Then you just call R local something like bracket GS enter. Then you will see all the possible rule for all the possible value of the design of the K will appear. Okay, how come this video stuck there? Okay, anyway, I guess there's a problem with the video, right? So this is another. But anyway, with MATLAB, we will visualize this. Okay, then in frequency domain, the best the specification of design is along this line, 100 degrees, something like that. Okay, so if you are lucky, you find the value of the key. If you are not lucky, A in is the extra transfer function. This is called lag compensator. You just need to know what is the ZP down the line, right? But here I'm going to show you an analytical way to determine this ZP. Then you will always find the solution. Okay, this is design method 4. But here you see we still use a PD controller, and this is a design method 3, design method 4. Then do a comparison for the same control system, right? So what should be the value for K? You see, this is design specification -1 plus minus G1. Is it in the direction of 135 degrees? You see, you get verified. This is in the direction of 135 degrees. Okay, so without the controller. That means when this guy go to 1, you see this is the response of the system. It's not stable to oscillation. But with the PB, this is the B means the derivative. In frequency domain is S, K1 plus K2S. You plug in inside here, then you have a look at the denominator, right? So you can say I want the zeta equal to 0.7 because the rule is here. Omega n is what? Square root 1 square plus 1 square. Okay, this is omega n, is the distance from here to here. You can compute zeta omega n. This guy is what? Omega n square, this is what? 2 zeta omega n. Then you can solve for Kp, Kp, right? So then this is the design solution for PD controller, right? Design method 3. Okay, then you use MATLAB, you see, very nice, right? So, but pay attention, overshoot is what? 20% overshoot, okay? Then use design method 4. We A in lag compensator. So we just A in this lag compensator. Then we write the denominator equation. Then replace this by this one. Then expand it. This guy has 3 root terms. This is polynomial equation of order 3. Then 2 of them in parallel occupied by this 1 plus minus G1, right? So you have okay, this is a design of the root by question. This is the extra rule, right? So you expand this multiplication, then you get this expression. For this to be equal means what? P must equal to 2 plus P0. K must equal to 2 plus 2P0. Kz must equal to 2P0, right? So you have this equality of a coefficient. So start with this guy, K equal to 2 plus 2P0. Then P0 is what? Shift this guy to here. K minus 2. Then both sides divide by 2. Then P0 equal to 0.5 K minus 1, right? Then now look at this guy. P equal to 2 plus P0. P0 is equal to this one now. Then replace P0 by this. Then you have a P equal to 0.5 K plus 1. Now look at this one. Kz. Kz equal to 2P0. Z equal to 2P0 divided by K, right? Then replace this one by this. Is a K minus 2. Both sides divided by K. It's 1 minus 2 divided by K. Okay. Then once you know P, you know Z, then you know the lag compensator. Good news is what you have extra parameter. That is a bonus. You can choose any value for K to get the equally good example, right? So you can verify with the 3 value of K, you have this kind of behavior. Then you see you can outperform a PD controller when K equal to 2 K equal to 2 K equal to maximum overshoot is very short, okay, less than 5%, right? And the PD is 20%. Okay, so this just help you to know method 4 is much better, right? Than PID. Okay, and this is also a demonstration. I hope it works. You see, with MATLAB, you can key in 3 functions, right? Then you run this program, okay? Then simulate, I see the simulate the step response, right? Then you know the equivalent of value tiers. Okay, good. Okay, so that's all for today's session. So we managed to finish today's study. Then we still have 5 minutes for Q&A. Okay, so the quick summary. So in today's study, we know what is a manufacturing system. Inside, we have a production system. Inside, we have an automation system. And inside, we have a control system. Then we know how to design a control system, right? Regardless what parameter to control, you can always use this 4 design method. By now, let you know what do we mean by this 1, 2, 3, 4. 1 system, 2 output, 3 KPI, 4 design method, right? Keep this in mind, then you will be comfortable, right? Then 5 means remaining question to be, but it's not 5. Then how to link all the component module inside a control system together or inside a robot together. Then the remaining 3 sections are tell you, right? How to connect sensor together, how to connect actuator together, how to connect controller together, so as to form a mini version of IoT inside the robot, mini version of IoT inside the production line. So inside the production line is also an IoT, yes, right? So actually, in future, you can think that every system is IoT, right? So then the remaining 3 sections is for you to know how to construct the system or network the system, which could be named as IoT, right? Here, okay. So by now you know what is a robot, what is automation system. Okay. Then next is how to construct network the system, which could be robot, could be automation system, or could be anything, anything inside your home. This is why when you do the mini project, actually your mini project must be IoT, okay, or network the system. Yes, right. Okay, any question? We have 5 minutes.